This lesson deals with some examples of phasor analysis. You can find these notes in the ECE202 ebook in Chapter 8, starting on page 18. Given this example with one voltage source, one resistance, one capacitance, and one inductance, can you find the current I sub s and the voltage V sub L as a function of time in steady state? Given that V sub s is 35 cosine 1000t plus 0, or just 35 cosine 1000t, R is 50 ohms, C is 10 microfarads, and L is 25 millihenries. I'm going to solve this example with a three-step algorithm. The first step is to transform the time domain circuit into the frequency domain. So our voltage source was 35 cosine 1000t plus 0. So the magnitude is 35 and the angle is 0. And I wrote down the value of omega here just to remind myself of the value of 1000. A resistor in the time domain is the same in the frequency domain, but a capacitor has an impedance of minus j over omega c. Omega is 1000, C was 10 microfarads, so I get a minus j 100. And the units on this is also ohms. The inductance is j omega L. Omega was 1000, L was 25 millihenries, so I get j 25 ohms. Now I want to solve for this current, which was I of s of t and V sub L of t, but in the frequency domain this becomes a phasor I of s and V of L. I'll put the broken arrow over them to indicate that it's a phasor. My second step is to perform a frequency domain analysis. Since I want to solve for this current, I could do that by finding the equivalent input impedance of this circuit and then taking that and dividing it into the voltage, just like we did in the time domain DC case. So what's the impedance looking in here? Well, I've got three things in series. I got 50 ohms, minus j 100 ohms, and plus 25 ohms. So when I add the real, it's just 50, and add the imaginary, and I get a minus 75 ohms. I'm going to do a division, so let me put this into polar form. So I'll punch this in my calculator, get out a magnitude and angle. I got 90.14 at an angle of minus 56.31 degrees. How does that seem reasonable? Well, this has to be longer than either of these two because it's the square root of the sum of the squares. The angle is going to be in the fourth quadrant because I have a negative imaginary part and a positive real part. This is longer than this, so the angle will be more negative than 45 degrees. So 56.3 seems reasonable. So I'll take the ratio now of V of s to Z equivalent. So 35 at angle 0 divided by 90.14 at angle minus 56.31. This ratio turns out to be 0.388, and then 0 minus a minus 56.31 is plus 56.31 degrees. Now that I know the current, I can find the voltage across the inductance by multiplying the impedance by the current. So I have an impedance of j 25 ohms times the current I of s. The j25 will be a magnitude of 25, and the angle is 90 degrees since we're right in the border of the first and second quadrant. You can also plug this in your calculator with a 0 plus j25 and you'll get the same result. The current we found over here is 0.388 at an angle of 56.31 degrees. So I'm going to multiply these two magnitudes. That turns out to be 9.707. We're going to add these two angles, and that's 146.31. The last step in our algorithm is to transform back into the time domain. We found that I sub s was equal to 0.388 at angle 56.31. So that'd be 388 milliamps at an angle of 56.31. All we're going to do is put the cosine of omega t between the two, and the units would be amperes. For the voltage, we had 9.707 at angle 146.31. It's going to put the cosine of omega t between the two, units are volts. It's just that simple. Take a look at another example. Let's model the Z equivalent of the last example at 1000 radians per second, and let's do it again at 3000 and 2000. Get some interesting results. Yeah, we found that at 1000 radians per second we had 50 minus j75. So this represents some R equivalent and some reactive equivalent. Now, this is just the 50 ohms that we started with, but this would be indicative of a capacitor. So if we set this equal to minus 1 over omega C equivalent, we could solve for C equivalent. So bring that over here, and we get the minus 75, canceling with the minus sign here, so you get 75 times 1000, and that's 13.33 microfarads. What that means is that you could replace this RL and C circuit with only one R and one C at 1000 radians per second, and you get the same equivalent impedance. Now let's repeat this at 3000 radians per second. So the capacitance is minus j over omega c, and that turns out to be now minus 33.3 ohms. And then j omega L, 3000 times 25 millihenries, you get a plus j75. When you add these two, I now get a positive 41.67. So that would be some equivalent reactance, but because it's positive, we could model it with an inductor. So we'll call this some omega L equivalent and then solve for L equivalent. So 3,000 radians per second, plugging in for omega, and we can just solve for L equivalent as 41.67 divided by 3,000. That's 13.89 millihenries. And again, you could represent that series RLC circuit with only one R and one L at 3,000 radians per second. Do the last case here of 2,000. Capacitance has an impedance of minus J over omega C, but now 2,000 times 10 microfarads, that turns out to be minus J50. For the inductance, it's J omega L, but now omega of 2,000 and 25 millihenries, I get plus J50. These two now cancel. And so I could represent this series RLC circuit with just one single resistor at 2,000 radians per second. Because the capacitive reactance and the inductive reactance are opposite signs, they can cancel. When they do, we call this resonance. And we'll talk some more about this a little bit later in this chapter. And these are some examples of phasor circuit analysis.